Let us now move on to consider the shape of molecules. We've been drawing electron dot structures. We've been largely ignoring these things that we call lone pairs. For example, you may recall that oxygen has two bonding electrons and two lone pairs that seem to go along for the ride, but they don't seem to do much of anything. Well, one of the things they do is they take up space. So when we're considering the shape of a molecule, we need to consider those lone pairs and account for the fact that they take up space. That's what this little chart is all about. Let us consider a linear molecule of the form AB2. All things being equal, those periphery atoms are going to try to get as far away from each other as possible. They've got an electron cloud around them. They don't want to be near each other. And so a linear shape is the way to go. And that's fine. We're going to consider once we start adding lone pairs to these molecules, and let's see what happens. If it's a three-petaled flower, isn't that a nice way to look at it? You can see that the bond angles would be 120 degrees apart. Even thinking in three dimensions, we cannot get things further apart. If this thing goes up, for example, it's not going to help. So it's a flat molecule. They call this trigonal planar, and that's its shape. Now imagine that one of these things was not, in fact, a separate atom attached, but it was simply a lone pair of electrons. That, in practice, is found to typically occupy even a little more space than if there were an atom there, and therefore you would have electrons there. In terms of the shape, these are ignored. After all, there is no atom there. So this is where the three atoms are. And since it occupies space, it's not trigonal planar. It's like trigonal planar with one thing removed. Take away a petal from the flower. What do you get? Bent. So this would be a bent shape. So if you come up with a molecule with a lone pair there, shape is bent. Tetrahedral is ubiquitous in chemistry, particularly in organic chemistry. Anytime you have a four-petaled flower, they tend to arrange themselves in three dimensions, right? Not just a four square, but they do it looks like what you'd call a pyramid, a three-sided pyramid. They call that a trigonal pyramid with a top thing. All the bond angles are 109.5 degrees, and that would be it. Now, if one lone pair existed, and it does, for example, in ammonia, NH3, well, that is going to push the bond angles down to a little bit smaller, 107 rather than 109.5. That shows up on a lot of tests, and that will give us that shape, trigonal pyramidal, right? Now, if you can have the possibility of two lone pairs here and here, and now it would push it down a little bit more, and you'd have a bent shape, and that's what water molecules are. I think they go down to about 105 degrees. See how it's a tetrahedron, but two of the things are just like taking up space. If you have five things distributed, it's interesting that it forms a trigonal bipyramid structure. So imagine a three-sided pyramid on the top and a three-sided pyramid on the bottom. This looks messed up. I don't like this linear shape. That should be a 120-degree bond angle right there. But that's trigonal bipyramid, and let's do some lone pair analysis. If one of them is lone pairs, it will come off the triangle in the center, the landing pad, if you will. This is sort of a triangular landing pad with a top and a bottom thing. One comes off that, and now you have what they call a sawhorse, sometimes also called the seesaw design, where that's the bipod for the seesaw, and it goes, and you play seesaw. So remember to take the lone pair off of the landing pad. That's what I call it. When you go T-shape, it also comes off of the landing pad, giving you just a T-shaped 90-degree bonding angles. Not necessarily what you predict, but that's it. And when all three go, it once again goes off the landing pad, and you get a linear molecule. So this is oftentimes asked because it's the weirdest ones. You have to know those little details. You don't want to take the lone pairs off the top and bottom. You want to take them off the triangle here that's flat. And let's call that the landing pad. That works for me. Octahedral is a beautiful structure. It's like two square pyramids on top of each other. And it's for like an AB6 type system, six-petaled flower in three dimensions. And the lone pairs would come off the square on the landing pad, first giving you what they'd call a square pyramidal structure. Can you see that that's a square pyramid? If you just rotate it down, it's like an Egyptian pyramid. add another lone pair, and take it off the same spot. And now it's just square planar, and once again, T-shaped. We're taking off the landing pad again and giving us the T-shaped, and if you took one more, it's now linear. Take-home message, always take your lone pairs off the landing pad central region for either a trigonal, bipyramid, or octahedral. I hope that doesn't sound too strange. That is molecular shape.